So welcome to lecture 22 of MCS 471, numerical analysis. So this review lecture aims to prepare for the first midterm exam this coming Friday, 15 October at 10 a.m. So this review also brings some focus to the course. So we have seen the fundamentals. So we started out with floating point numbers and floating point arithmetic, which is quite different from the real number arithmetic. And we have considered three problems: root finding, linear system solving, and data fitting. Either fitting, representing data via interpolation, or solving in the least square sense. So the focus of this review will be on some of the major questions that you may encounter on Friday. So, but let me first explain how the midterm will occur. So the midterm will occur this Friday online. So it is during our class meeting at 10 o'clock. It will last 50 minutes, also the entire duration of our meeting. What is important, and I will emphasize this at least one or two times, that it's your decision. So there's a first deadline, and today is 13 October. That's Wednesday, 13 October, the date of this lecture. So by 5 o'clock of that day, I must receive an email if you will do the exam. So there is the skipping policy. So the exam is not compulsory. If you are not prepared sufficiently for this exam, then it might be a good decision to postpone. So that's the first important thing about the exam. So there is a deadline, a first deadline, where actually you have to decide whether you can study for the course or not, for the exam or not. The exam is individually, so we are using Julia, and that is still sufficiently original. So I think external sources may not help you that much, but the internet also means help from qualified individuals. So that is plagiarism. So as all our computer projects, all the homework, our solutions, your solutions should be in a Jupyter notebook with a proper Julia kernel. So the exam lasts 50 minutes, and I'm sorry, the PM is actually the AM here, so you do not have the entire day. So I will, there's still a bug on the slide. So you have 50 minutes. There is a 10-minute grace period. So sometimes the internet might not collaborate with you. But internet outages never last longer than a couple of minutes. So do not wait till after the 10:50 has passed. If you have seen the questions and do not submit on time, then it will be as if you did not take the exam, as if you didn't skip the exam, but you have a 0 score on the exam. So not submitting on time will incur a penalty. All right, so these are the most important things. So this course is on numerical analysis, not on programming. If you learn programming, then actually all the better. But you will not be asked to write code, although you may have to define sometimes something. So the questions on this review are, so the review is structured in 4 parts. We have covered a lot of algorithms. So the next slide will actually give you a more exhaustive picture, but it's actually mainly important that you have some computational skills and insights. So if you have done the homework and if you have done well, then you should actually be prepared. Same with the projects. We had thus far already 2 projects that are on running, observing, and explaining. If you are good at that cycle, then you should do well on the exam. All right, so here is a little bit more exhaustive overview. So you could see that we have seen many algorithms. So numerical analysis is the study of algorithms for continuous problems. We have seen the root finding, the bisection method, then the secant method, the regular falsi, combines bisection and secant, and then Newton's method if you can do derivatives. Optimization runs also through. So we have seen our first optimization method with the golden section search, but then we also applied it when we looked at iterative methods, in particular the conjugate gradient method. That was the first time when we encountered the steepest descent. And we have also seen methods to approximate. So we have the interpolation methods, and then we have the rational approximations, the more geometric oriented orientations with the cubic splines, and then we have the least squares fitting. So actually one can see the last chapter entirely on, again, the representation of data. But linear algebra occupies at least half of the material what we have covered. So we had 1 chapter on solving linear equations. So these algorithms in the 4, 5, 6 category fall within linear system solving. The direct methods, the iterative methods, and then the methods for the positive definite problems. We ended also with linear, solving linear problems again, but then in the least square sense, starting with DQR factorization that we can do via Gram-Schmidt and Householder. Then we have the iterative generalized minimum residual method. And then we ended with Gauss-Newton as an application and Diefenberg-Markar as a hybrid. The power method is a way you could see to compute the spectral radius of a matrix. And that brings us then very much again to the beginning of the linear algebra section, where we started with vector and matrix norms. So this is an overview of the algorithm. So one can see numerical analysis as the study of algorithms for continuous problems. In this review, we cannot review all the algorithms. For preparing for the exam, it's kind of important that you have organized your materials. In using materials from the internet, it would already be very good if you have everything downloaded that is on the course website, if you have it on your computer. That will save you time. And make sure that if you are looking for a function that, for example, does Neville interpolation, that you do not need to run through all the 21 lectures, that you have to not do some clicking, pointing and clicking all the time, that you lose 5 minutes or more locating the right function that you have to use. So be organized. Before we dive into the review questions, an important point again. So this is again the deadline. If you are looking at these recording after 5 p.m. on Wednesday, 13 October, then you missed the deadline. And then you will automatically skip the midterm exam. That's how it goes. So in a way, this is not a course where if you see the questions with common sense, you will be able to solve them. Some of the question you may be lucky, but not in all the questions. So please be prepared. So that deadline, that very first deadline is there. It is an online exam, so without notifying me that you will take the exam, you will not receive the questions. So that's very firm here. The skipping deadline, the skipping policy also means that it doesn't mean that you feel very bad when you get the grade back and you can drop the score. So this is also important. This may factor in your decision. An exam, if you feel that you understand everything, and if you get a 20 out of 100, that may be your reality check. So in that sense, it could still be good to give you that insight, but it's an expensive one. So I also hope that, so there is I will run through the slides which have answers on them, but I will also post a version of the review without the answers. So one way to prepare also for the midterm exam could be to try the review questions honestly without looking first at the answers. So actually pausing now the recording and go to the questions that are posted on the site before looking at. All right, so let us now look at the first question. The review questions have many parts in them. So the questions do have several parts in them. So here is a question that consists in several parts. So on the exam, you may have one of these three. So let's look at these questions. So we have a floating point number system with limited accuracy, only 3 digits in the fraction, and the exponents are ranging between -1, -11, and 11. So the question is then, what is the machine precision? How many positive numbers are there? Remember the slide on the number system. And how does now an addition work in floating point arithmetic? All right, what is the machine precision? Here I'm answering this in 2 steps. There is the basis that one has to use, the base, and the number of 3 in the fraction. So to answer this question, there is too much information in the first sentence. So the range of the exponents actually does not factor in here. So there is the formula that you have to evaluate, and that gives you the machine precision of 10 to the power minus 3. The minus is important. Yes, indeed. You would need to use the exponents if the question would be, what is the smallest positive number that can be represented in this representation? So the second question is, how many positive numbers can you represent? And by positive numbers would be here valid numbers. So we are assuming that every number is normalized. With the smallest positive number, you do have the unnormalized number. So the smallest unnormalized number that you can represent. So in a way, this is base 10. We have answered these questions also with Julia, but there it's not base 10. I would also say here, one is tempted to use now in these questions as much as possible the technology, but the phrasing with the decimal number system is actually good to force you to see whether you have some insight in this floating arithmetic. All right, so we have, how do we solve this problem? Well, we have 3 digits, but the normalization means that the first one after the dot always needs to be non-zero. So actually in the bits it always has to be 1, but that means that for A we have 8 choices. So this is where we get to the 8 here. For the B and the C we have more numbers. So our fraction actually ranges from 0 to 9 for the B and the C. So you can see how many numbers you can make. You subtract, you could also, this reasoning could be different. You subtract all the unnormalized numbers. Okay, so these are all the fractions. Then we have all the possible exponents that we can make. So the exponents range from -11 to 11. So we have 22, but the exponent can also be 0. So we have 23 different values. So this actually gives us the number line, all the positive numbers that we can make, that consists of 20,677 positive numbers. All right, so floating point arithmetic. We have this number system where we add 2 numbers. One is an integer number, the other one has 2 decimals after the dot. One is larger than the other, and we will first represent these numbers in the number system. So that means that the 12,345 gets abbreviated to 123 and then with 2 zeros after. We do not also lose accuracy when we are representing the first number. We are rounding. So here it so happens that the 4 and the 3 are less than 5. If the 3 would have been a 5 or higher, it would have been 219 in the fraction. That's the first important step, the representation in that number system. It is decimal. Then we do the denormalization of the smallest number. So notice the exponents 5 and 3. So we must see everything in exponent 5. So everything is here done. We focus then on the fraction. And then we do the addition. So here it might be again to use technology, but if you do so, do this with the integer arithmetic. So because the computer works with binary and 0.1 cannot represent it exactly. So that's also the reason why there is actually in certain accounting applications, there is a decimal floating point number system. So there is decimal, there are people who actually do. So decimal arithmetic is used in accounting, but not in this technical engineering course. All right, only then round. So it would be a mistake. So here you would not make a mistake, but again, suppose that this would be 2,9 instead of the 1, then actually you would have to round. Here the rounding is again only chopping. So we do the rounding at the very last step when we represent again the results. And then it's good to write also what the sum is in this number system. All right, so this is the first question. All right, so let's now move to away from the fundamentals to the first problem that we considered, the root finding problem. And here you see the methods that we have covered, the most important methods, bisection, secant, and Newton. The purpose of this exercise is here that you can do 4 steps with these methods. In this course, I would only ask one of them. On the actual exam, you would only have one of them. You would need to locate, to prepare for this, you would actually need to locate the code for this. And then also there would be a follow-up question, what is the accuracy? So we measure the accuracy in terms of the residual and the forward error, the estimate for the forward error. All right, let's move on to the next method. So this is a question that asks you also to set up the equation now. We want to run Newton's methods to compute the cube root of a number given with 4 decimal places of accuracy. So then it makes sense to actually compute also up to 4 places of accuracy. So there are 2 things that one needs to do. One needs to recognize that there is an equation that is being solved, and one must then also set up Newton's method for this problem. So you could look into the function that we have defined. And the third step is that you kind of need to know how many steps you need to do to get 4 decimal places of accuracy. All right, the first important step is to know that we are solving a cube root. We have a symbol for that, but actually there is no cube root function, so you have to do this with an equation solver. And the other issue is that where do you start? So we have seen the cobweb diagrams for another problem like this, and actually using x naught equal to the number itself is actually quite fine here. So the formula we are going to execute via a Julia function. So we do this a couple of times. And actually, you look at the first 4 decimal places that you see here. First 4 or 5. If they no longer are changing, you can stop. And indeed, when we check the accuracy, so there is the forward error. You check when the numbers are no longer changing. When we defined more seriously the function, in general, we were actually computing the d of x. So that's the d of x, the absolute value of the d of x will actually tell you the accuracy or the estimate for the forward error, so an absolute value. Here you will see that if you run this a couple of times, the first 4 or 5 decimal places no longer change. And you can a posteriori verify the accuracy by computing the backward error. And that means that we actually are evaluating the equation again. You could do this explicitly by plugging into the equation, but here we did it by inspection. So here we see that we have 27.13, even if we take 1 more decimal place. So our answer has to be represented in 4 decimal places. So we do have 4 decimal places of accuracy. So this is the f of x. And this is the estimate for the backward error. How much should you change the input for the computed problem to be the exact problem? And here you see that for the 3.005, you may have to change the last 3 into a 4. And if you would give the answer to 5 decimal places, then the rounding would be correct. So you would be 27.13. But in any case, this is the answer to this question. The answer. But so giving numbers is only half of the question. So you must show your work, and it's not just looking and producing numbers that is important here. Case in point, so I can give you the output of a calculation and then ask you to a particular question about this. Here is the question, another question, so the question at the bottom is here, but there are alternative questions. Instead of asking what is the multiplicity, you can also ask what is the order of convergence. And you will actually see that it takes here 4 steps, here more steps, about the same steps here, to actually get 1 decimal place of accuracy. So the forward error moves extremely slowly. The backward error is actually a bit faster. But still, if you use that as a measure for the accuracy, you still need 2 decimal places and 2 steps to gain 1 decimal place in your backward error. And it is a singular problem. With the regular problems, forward and backward, they coincide. When things start to get, in case of multiple roots, you have to make a choice. So here you can see that in this calculation, with the backward error, we can go close to the machine precision, which means that that computed result, and you can see it's very bad, we need 1. So the support started with this. So we have 1 the root. So the error in the output space is quite large, but the error in the input space is quite small. So that's the best that Newton's method can do. But you can improve it knowing that the rate of convergence is geometric when Newton's method converges to a multiple root. And that we can exploit to estimate the multiplicity. So what is m? It is 4. The 4 is not the 10 to the power minus 4, but the 4 is computed by taking the ratio of 2 consecutive errors. So it should be close to 3 over 4. And indeed, we find 0.75. So we have 2 consecutive errors when we compute them. So here I computed the errors from the 1, but I could actually also have taken the ratios of these here. So they also would have sufficed. But here I use the actual error. The error computed by computing the difference with the exact root. And you see if they have the same exponents, and we have the 3 over 4 coming in. And that allows me to justify the answer m equals 4. All right, then another question that for which you will need to use the code for the copy diagrams. So we have a number of fixed point iterations, and I can tell you what the answer is for the third one. This actually is computing the square root of 5. The square root of 5, a good algorithm, and we actually are trying to compute the square root of 5 also by actually using the square root function. So what we have is we are trying several fixed point iterations to compute the fixed point. I'm sorry, so it's not the square root of 5. The fixed point is actually 5. All right, so you can recognize this here very clearly with 5 times 5, the square root is 25, so you will have the left 25. So which iterations will be best? All right then. Here is another conceptual question that does not require that much computation. Suppose you have already a good enclosing interval for a function that has one minimum. So this function here is unimodal. Then how many additional function evaluations would you need to improve the accuracy to 2 decimal places? And it's important that you justify. So now from the golden section method is that we start with 2 function evaluations. So if you do your initial step, you will be at least 2. But we also know that in every step, the length of the interval gets reduced with a constant factor. So after the first step, we need 2 function evaluation, but then after the next step, we are going to gain accuracy with 1 extra function evaluation. So you could solve this essentially also by experimentally. So here I do the justification with the ratio of 0.6. But you could also take the function that we have posted and that is posted, and you can run the function and then see at the end. So you have to adjust the tolerances and then see how many function evaluations will suffice. So the length of the interval should be 100, and we actually are computing the c to the power n, and this actually indicates the number of steps that you do. So we are solving an equation, we're solving this equation here that can be solved with the logarithm. Right. It doesn't matter which logarithm that we use because we divide the logarithms and we take the upper bound. All right, we are moving into linear algebra now, solving linear systems. So these questions are very exhaustive. So you would, on an example, have only 4 questions, and you would typically not have an entire set of questions like this. I would like to point out that this was also asked for the exercises. Partial pivoting and row pivoting are the same. We speak of row pivoting because we interchange rows. We speak of partial pivoting because we do swap columns. So the complete pivoting would be also that we are doing the column interchanges. So what is the scaling now? Well, we've done some scaling when we did the preconditioning with the iterative methods. One can also scale by, and in some sense this is to make up for the partial pivoting. You can scale by dividing every equation by the largest number that you see. So, and here the largest numbers occur in the right hand side. So that is to make up for the scaling. This implicits, so you can scale as you go equation by equation. You can also do explicit scaling on the entire system. We have 3 different decompositions that we get there, depending on how scaling, and then you can solve the systems 3 times. The question is here, do you see any difference essentially? The numbers might be still too large for this, but we are working with 4 decimal places here as well. One can then check is also to compute the determinant from the LU decomposition. And we can see then also the computation of the condition number. Is this a well-conditioned number if you compute the condition number? We can compute for a regular system, we compute the inverse. And then with the one norm, one can compute the condition numbers. All right, one of the exercises we had the special Koleski factorization without taking square roots. Tridiagonal matrices are also special. Assume that the matrix is also diagonally dominant, so the elements on the diagonal are larger or sufficiently large enough, far away from 0, then you do not need to do any pivoting. So there is a special LU decomposition one can write for such matrices. And the nice thing about this special LU decomposition is that it will be linear in the size of the problems. So actually you can represent this tridiagonal matrix by 3 vectors. Its LU decomposition also consists of 3 vectors. So later in the course, we will actually see how these matrices arise when we get to partial differential equations. All right, I have the answer for this question. And this question we have encountered already in an exercise or also in the last project. So we have a numerically computed solution, and it's computed with a working precision of 30 decimal places. How would you verify that? What is the backward error? Now, suppose somebody would tell you you have computed with 32 decimal places, but the condition number is 10 to the power 12. Now, how many of those 32 decimal places can you be sure of can be correct? And how do you estimate the forward error using that justification? All right, what is the backward error? Well, you compute the norm of the residual vector, or short, the residual. This makes that this is the first check that we essentially always do when we solve a linear system, if it is a square one. If we solve it in the least square sense, then we take the residual vector and we check if it's perpendicular to the column space of the matrix. But here for this question, you compute the residual. How many of those 32 decimal places are correct? Well, we have a condition number of 10 to the power 12. The back of the envelope calculation is subtracting from the 32 the 12 and doing the 20. How this computation works is following the inequality. So we have 10 to the power minus 32 for the accuracy. So here it is represented in decimal places. We multiply this with 10 to the power 12. The reasoning being that we have our matrix represented correctly up to the machine precision. So a modification of this problem would be, suppose that the number of the matrix, if the data, if the coefficient matrix was somehow corrupted, if you would know only 10 decimal places, then you could see that there would be no hope to have any accuracy with a 10 to the power 12 matrix condition number. All right, the final answer is this. The justification lies in the inequality. And then how can you improve, how can you estimate the forward error? Well, this is where iterative methods come in nicely. We can use the method of Jacobi. We are then essentially taking the residual vector again, but scaling it, dividing all its components by the elements on the diagonal. So here is the computation. This is if you would be using the forward error, and if you would be using the method of Jacobi. And in some sense, it would make sense if you have again observed data that is accurate up to 10 decimal places. You would actually then improve the answer by working with a more accurate version of your input problem. All right, so far we have seen 9 questions, but only essentially 2 chapters, or 2 of the 4, so I still have 5 minutes left, so I have to hurry up. Question 10 is again overview question, where we have the algorithms, the divided differences that we apply on a polynomial. So the explanation, so there was an exercise on that. So the explanation why the last divided difference here should be 0 is because we are working with 4 points on a polynomial of degree 2. A polynomial of degree 2 is interpolated correctly and exactly with 3 points. So this is also the application of the next term rule. So we are using the divided difference, the last divided difference, to decide whether we need one more point or not. We can also see this in the least square sense, where we want to approximate our, see whether the data following the trend as prescribed by the polynomial, if it goes upwards or downwards. All right, fitting data. One has to decide what is the best degree. Well, you look at the shapes. At the left, you see a very linear shape. At the right, you have a shape that is more following a parabola, going down and going up. So consequently, at the left, the best might be a linear fit. The right fit, the best fit might be a quadratic fit. So the question is to define the setup. So we reckon, so this is the answer here. So also the answer is given with the fit. So the blue line goes approximately through the red points. And the setup of fit for the linear fit. For the linear fit, we look for the coefficients, the slope and the intercept of a line. So we solve for 2 numbers. For the quadratic, we solve for 3 numbers. So we have a larger matrix with 1 extra column. All right, I have 1 question left. Going to the previous lecture about the power method. Can you converge quadratically with the power method ever? The answer is no. But it's the justification that matters. And the justification is actually in the ratio of the eigenvalues. So the eigenvalues are fixed. So you have a fixed number of steps you have to go through to gain 1 decimal place. So it could be that in 1 decimal place you're getting 5 So that fixed number could be a fraction. So you've seen last lecture that we can fabricate matrices with prescribed eigenvectors, eigenvalues, also eigenvectors, but it is important that convergence is not quadratic. What does it mean to be quadratic is that you have an exponent in the ratio in a quadratic, but the ratio between two consecutive errors. If you take that ratio, you will have the fixed, you will also see a fixed step. So quadratic convergence means you have a doubling of the decimal, or of the correct decimal places in every step. Okay, so the way you phrase it is in your words, but there are two ingredients that are important in this answer. The ratio of the eigenvalues and also the definition of quadratic convergence needs to be in there. All right, the last important question, there is always so much more. So the questions that I try to answer in this lecture are representative, but they are certainly not exclusive. And also there will be, therefore, many versions of the midterm exam. I will stop here.